Good afternoon, everyone. My name is Koren. I'm a PhD student at the Department of Mechanical and Industrial Engineering at NTNU in Norway. And today I'm going to present on correlating the hydrogen gas charging with electrochemical charging using the hydrogen permeation technique. So the outline of my presentation is that I'll go through the objective and the method. I'll explain the experimental work, show some results before I summarize. So this work is part of the Hagen project, which is a research project in cooperation with SINTEF, NTNU, Kyushu University, and sponsored by the Research Council of Norway, and have several industrial partners. So the main aim of this project is to investigate whether low alloy steel pipelines are suitable for transportation of pressurized hydrogen gas, and especially whether low alloy steel pipelines, that's the subsea network in the North Sea currently that's used for natural gas, whether it can be used for high pressure hydrogen gas. So the project consists of different work packages. I'm in this work package 1, investigating hydrogen uptake and diffusion, but we also have work packages on micromechanical testing, macromechanical testing, and modeling. So to use these pipelines for hydrogen gas, we want to do a thorough mechanical testing to test the hydrogen susceptibility, and you want the testing conditions to be similar to your operating conditions. But testing in high pressure hydrogen gas comes with safety concerns and requires advanced lab infrastructures. So instead, often electrochemical charging is used as a substitute. We want to know what is sort of the equivalence between electrochemical charging and hydrogen gas charging in terms of severity of the environment. So the main aim of this work is to determine the hydrogen gas pressure that produces the same hydrogen uptake as electrochemical charging conditions. So I'll quickly go through the method. So the basis is that we consider that two charging conditions are equivalent if they produce the same subsurface hydrogen concentration in a steel. And so to determine the subsurface hydrogen concentration, we use the hydrogen permeation technique. And I'm sure most of you are familiar with the technique, but I'll just quickly go through the basics. And so the basic is that you have one charging cell and one detection cell separated by your sample. And so in the charging cell, you can have either hydrogen gas or electrochemical shown here. So here you would impose a cathodic potential or current density so that you evolve hydrogen on the surface. It will absorb and diffuse through your sample. And in this detection side, you will apply an anodic potential so that once the hydrogen reaches this surface, it is oxidized, and the oxidation current is a measure of the hydrogen flux through your sample. So the result will look something like this. You have this S-shaped curve, and on the y-axis you have the permeation current density or hydrogen flux, and you have the time on the x-axis. And from this curve you can determine the diffusion coefficient and subsurface hydrogen concentration. For example, by this time lag method, which is based on the time it takes to reach 63% of this permeation current density at steady state. And you can use this equation. And we call it as effective as traps can affect the transportation of hydrogen through your sample. And then we can use this effective diffusivity together with the steady state permeation current density to calculate the subsurface hydrogen concentration, in this case in lattice and reversible trap sites. So to the experimental work, the steel we are investigated is X65 pipeline steels, and that's taken from a hot rolled and welded pipe. And the microstructure consists mainly of ferrite, about 85%, and also some perlite and bainite. So our gas permeation setup looks like this. It's a high pressure hydrogen gas apparatus where we have a charging autoclave that's filled with hydrogen gas, and we apply 3 different pressures: 10 bar, 50 bar, and 100 bar. We have our sample here in the form of a plate, and it's coated with palladium on both sides to ensure hydrogen uptake on the charging side and hydrogen oxidation on the detection side. In this chamber, we have 0.1 molar sodium hydroxide solution and apply an anodic potential of 300 millivolts versus the saturated calomel electrode. In electrochemical charging, it is the similar sort of setup, but instead of having an autoclave here, we have an electrochemical cell filled with 3.58% sodium chloride, and we apply 3 different current densities: -1, -15, and -50 milliamps per centimeter squared. And in this case, we only have palladium on the detection side. So to the results, our hydrogen permeation, gas permeation looks like this. We have the permeation current density and the time axis, and we can see that this is the 10 bar, 50 bar, 100 bar curves. So the steady state permeation current density or flux of hydrogen increases with the charging pressure. In the electrochemical hydrogen permeation results, we see the similar trends. The hydrogen permeation flux is increasing with increasing charging current density. So now I'll go through the method of determine this equivalent charging pressure, and it's a method that's adopted by Venezuela in his co-workers in this paper. So we take the gas permeation results that we have, and from these, oops, that was the wrong way, we calculate the subsurface hydrogen concentration. And then we plot the subsurface hydrogen concentration versus the square root of the pressure. So concentration versus square root of pressure. And you can see that the points falls on this linear line, which is in accordance with Sievert's law, which states that the hydrogen concentration equals the solubility constant times the square root of the hydrogen fugacity, or the hydrogen pressure at low pressures. So then we use this plot, and we can extrapolate this line, and we take the results we have from electrochemical permeation. We calculate the subsurface hydrogen concentration, and we superimpose the results of the concentration onto this line. So you can see the points here. So then we can, so for example, this first point corresponds to this -1 milliamp per centimeter squared charging. And then we can take this point now and read it off the sort of equivalent charging pressure, which would be 45 bars. So it would mean that if you want to represent the same hydrogen concentration with electrochemical charging as 45 bars would give you, you could charge at -1 milliamp per centimeter squared. And then we can calculate the same thing for the other 2 charging conditions, which -15 milliamp per centimeter squared would be equivalent to 90 bar, and -50 milliamp per centimeter squared would be equivalent to 167 bars. So by this method or calculation, we can determine more this equivalent electrochemical charging that you could use to represent the gas charging if you want to operate a high pressure gas pipeline, for example. So to summarize, we have used this hydrogen gas permeation and electrochemical permeation to determine the subsurface concentration, and have used the relation with Sievert's law to calculate the equivalent charging pressure of certain electrochemical charging conditions. Thank you for your attention.